Book 9, Chapters 7 and 8 of 10 books on architecture. This LibriVox recording is in the public domain. Recording by Fredrik Karlsson. 10 books on architecture by Vitruvius. Translated by Morris Hickey Morgan. Chapter 7. The analemma and its applications. 1. In distinction from the subjects first mentioned, we must ourselves explain the principles which govern the shortening and lengthening of the day. When the sun is at the equinoxes, that is, passing through Aries or Libra, he makes the gnomon cast a shadow equal to 8/9 of its own length in the latitude of Rome. In Athens the shadow is equal to 3/4 of the length of the gnomon, at Rhodes to 5/7, at Tarentum to 9/11, at Alexandria to 3/5, and so at other places it is found that the shadows of equinoctial gnomons are naturally different from one another. 2. Hence, wherever a sundial is to be constructed, we must take the equinoctial shadow of the place. If it is found to be, as in Rome, equal to 8/9 of the gnomon, let a line be drawn on a plane surface, and in the middle thereof erect a perpendicular, plumb to the line, which perpendicular is called the gnomon. Then, from the line in the plane, let the line of the gnomon be divided off by compasses into 9 parts, and take the point designating the 9th part as a centre to be marked by the letter A. Then, opening the compasses from the centre to the line in the plane at the point B, describe a circle. This circle is called the meridian. 3. Then, on the 9 parts between the plane and the centre of the gnomon, take 8, and mark them off on the line in the plane to the point C. This will be the equinoctial shadow of the gnomon. From that point, marked by C, let a line be drawn through the centre at the point A, and this will represent a ray of the sun at the equinox. Then, extending the compasses from the centre to the line in the plane, mark off the equidistant points E on the left and I on the right on the 2 sides of the circumference, and let a line be drawn through the centre dividing the circle into 2 equal semicircles. This line is called by mathematicians the horizon. 4. Then take a 15th part of the entire circumference, and, placing the centre of the compasses on the circumference at the point where the equinoctial ray cuts it at the letter F, mark off the points G and H on the right and left. Then lines must be drawn from these and the centre to the line of the plane at the points T and R, and thus one will represent the ray of the sun in winter and the other the ray in summer. Opposite E will be the point I, where the line drawn through the centre at the point A cuts the circumference. Opposite G and H will be the points L and K, and opposite C, F, and A will be the point N. 5. Then diameters are to be drawn from G to L and from H to K. The upper will denote the summer and the lower the winter portion. These diameters are to be divided equally in the middle at the points M and O, and those centres marked. Then, through these marks and the centre A, draw a line extending to the 2 sides of the circumference at the points P and Q. This will be a line perpendicular to the equinoctial ray, and it is called in mathematical figures the axis. From these same centres, open the compasses to the ends of the diameters and describe semicircles, one of which will be for summer and the other for winter. 6. Then, at the points at which the parallel lines cut the line called the horizon, the letter S is to be on the right and the letter V on the left, and from the extremity of the semicircle at the point G, draw a line parallel to the axis extending to the left-hand semicircle at the point H. This parallel line is called the logotomus. Then centre the compasses at the point where the equinoctial ray cuts that line at the letter D, and open them to the point where the summer ray cuts the circumference at the letter H. From the equinoctial centre, with radius extending to the summer ray, describe the circumference of the circle of the months, which is called Menneus. Thus we shall have the figure of the analemma. 7. This having been drawn and completed, the scheme of hours is next to be drawn on the base plates from the analemma, according to the winter lines, or those of summer, or the equinoxes, or the months. And thus many different kinds of dials may be laid down and drawn by this ingenious method. But the result of all these shapes and designs is in one respect the same, namely, the days of the equinoxes and of the winter and summer solstices are always divided into 12 equal parts. Omitting details, therefore, not for fear of the trouble, but lest I should prove tiresome by writing too much, I will state by whom the different classes and designs of dials have been invented. For I cannot invent new kinds myself at this late day, nor do I think that I ought to display the inventions of others as my own. Hence I will mention those that have come down to us and by whom they were invented. Chapter 8. Sundials and Water Clocks. 1. The semicircular form, hollowed out of a square block and cut under to correspond to the polar altitude, is said to have been invented by Berosus the Chaldean. The scaff or hemisphere by Aristarchus of Samos, as well as the disc on a plane surface. The arachne by the astronomer Evdoxus, or, as some say, by Apollonius. The plinthium or lacunar, like the one placed in the Circus Flaminius, by Scopinas of Syracuse. The prosta historomena by Parmenio, the prospanclima by Theodosius and Andreas, the pelesinum by Patroclus, the cone by Dionysius Dorus, the quiver by Apollonius. The men whose names are written above, as well as many others, have invented and left us other kinds, as, for instance, the conarachne, the conical plinthium, and the antiborean. Many have also left us written directions for making dials of these kinds for travellers, which can be hung up. Whoever wishes to find their base plates can easily do so from the books of these writers, provided only he understands the figure of the analemma. 2. Methods of making water clocks have been investigated by the same writers, and first of all by Ctesibius the Alexandrian, who also discovered the natural pressure of the air and pneumatic principles. It is worthwhile for students to know how these discoveries came about. Ctesibius, born at Alexandria, was the son of a barber. Preeminent for natural ability and great industry, he is said to have amused himself with ingenious devices. For example, wishing to hang a mirror in his father's shop in such a way that, on being lowered and raised again, its weight should be raised by means of a concealed cord, he employed the following mechanical contrivance. 3. Under the roof beam he fixed a wooden channel in which he arranged a block of pulleys. He carried the cord along the channel to the corner, where he set up some small piping. Into this a leaden ball attached to the cord was made to descend. As the weight fell into the narrow limits of the pipe, it naturally compressed the enclosed air, and as its fall was rapid, it forced the mass of compressed air through the outlet into the open air, thus producing a distinct sound by the concussion. 4. Hence, Ctesibius, observing that sounds and tones were produced by the contact between the free air and that which was forced from the pipe, made use of this principle in the construction of the first water organs. He also devised the methods of raising water, automatic contrivances, and amusing things of many kinds, including among them the construction of water clocks. He began by making an orifice in a piece of gold or by perforating a gem, because these substances are not worn by the action of water, and do not collect dirt so as to get stopped up. 5. A regular flow of water through the orifice raises an inverted bowl, called by the mechanicians the cork or drum. To this are attached a rack and a revolving drum, both fitted with teeth at regular intervals. These teeth, acting upon one another, induce a measured revolution and movement. Other racks and other drums, similarly toothed and subject to the same motion, give rise by the revolution to various kinds of motions, by which figures are moved, cones revolve, pebbles or eggs fall, trumpets sound, and other incidental effects take place. 6. The hours are marked in these clocks on a column or a pilaster, and a figure emerging from the bottom points to them with a rod throughout the whole day. Their decrease or increase in length with the different days and months must be adjusted by inserting or withdrawing wedges. The shut-offs for regulating the water are constructed as follows. 2 cones are made, one solid and the other hollow, turned on a lathe so that one will go into the other and fit it perfectly. A rod is used to loosen or to bring them together, thus causing the water to flow rapidly or slowly into the vessels. According to these rules and by this mechanism, water clocks may be constructed for use in winter. 7. But it proves that the shortening or lengthening of the day is not in agreement with the insertion and removal of the wedges, because the wedges may very often cause errors.